the introduction. Also, thank you for the invitation, which goes both to Sanju and Hong. We're over there. I haven't seen you. And when I was thinking about the topic, I was thinking I should do an overview talk or maybe like a talk more focused on some result. And this is a talk which is a little bit more focused on a particular result. And I must say that after the couple of hours of discussions today, I am worried that it might be like somewhat on the boring side for half of you, because I guess it will be mostly concerning the topics we discussed. And but I didn't want to like switch the topic to what has been announced, and I just stick to this one. So it's a joint work with my former student, now an assistant professor at Czech Technical University, Konzavolec, and with Fanway, she's a postdoc at Princeton and soon moving to a tenure track to Duke. And this has been a work which was spanning quite a longer period of time, and which is also witnessed that it's still ERC supported, or it was ERC supported even if my ERC grant has already ended. But I'm obliged to announce the support which I'm doing at this point. I don't know if anybody looks at these videos, but in case somebody does, so it was announced. So this talk will be about something which some people call the Ramsey multiplicity, and I want to recall the classical result which gave the name, which is the Ramsey's theorem, and that says that if I have a 2H coloring of a sufficiently large complete graph, then of course in that 2H coloring I can find a monochromatic copy of any complete graph. So the quantification is that for every small k where exists R depending on k, such that every complete graph on R vertices contains a monochromatic copy of the complete graph of k vertices. And as we know, up to some maybe lower order terms, these are the two bounds that has been standing unchallenged for a long time. So the upper bound just comes from the inductive argument, and the lower bound just comes from considering a random coloring. And there have been a recent breakthrough result due to Campos, Griffiths, Morris, and Saharas. Julian's name is difficult. Saharas Budhe, and in their breakthrough paper, they actually improved the upper bound. So now the base of the exponent is not 4, but it's 4 minus epsilon. And in the abstract they have epsilon, but I look at their paper, plug in a couple of estimates, and unless I mess it up, this is the bound weight. Okay. And proving like this was the asymptotic, and for small values, actually it's quite difficult to compute. And there's this Fermi quote which is attributed to Erdős, which says that we know there are 3. Ramsey number for 3 is 6, we know R4, but already R5 is unknown, but he's saying that if there is this aliens, like the aliens are landing on the Earth, and they come to us and demand the value of the 5th Ramsey number, and if we don't provide the correct answer, it will be destroyed, then we have a chance. Like we put all the mathematicians together, we bring all the computers together, and humankind will be saved. But if they decide that what they want is the 6th Ramsey number, then mathematicians will be useful, but useless. Sorry. But what we should do is we should just prepare to fight regardless how powerful they are or not. So computing Ramsey numbers, the small Ramsey numbers, is difficult, and there's a reason I put this quote. First of all, I want to say this problem is challenging, but for a long time we had these values. So we had these are the values I was mentioning. The third one, fourth one is known. For fifth one, we have upper bound. For sixth one, this was the lower bound and the upper bound. And there's a recent progress, which perhaps may be viewed as going to save the humankind in the unlikely event of the aliens landing on the Earth. And that's an improvement due to Sergei Dorein, Jeremy Turkot, and Konzavolec. And they managed to kind of maybe shave about like 1/4 of the interval. So they went from 161 to 147. So there has been a lot, both in the asymptotic and also like on the specific values done recently. But in this talk, I want to look at a different problem. So as I mentioned, I want to be looking at the problem of Ramsey multiplicity. And in Ramsey multiplicity, I'm asking what is actually the minimum number of the monochromatic copies of a particular graph. So if I look at the original theorem of Ramsey, I will be asking what is the minimum number of the copies of Kn. And so let's look at triangles. So there's a clear upper bound. So I'm asking what is the minimum. So to get upper bounds on the minimum, I need to provide constructions or at least existential proof. And what I can do is if I take a random coloring, so if I randomly color the edges of a complete graph on capital N vertices with two colors, the probability that a particular triangle will be monochromatic is 1/4, because so let's say I color with red and blue. With probability 1/8, I will see red triangle. With probability 1/8, I will see blue triangle. With probability 1/4, I will see a monochromatic triangle. So the answer to this question is at most this number, because like if this is the expected number of monochromatic triangles, there is a coloring achieving at most this number. And for the lower bound, there's a theorem of Goodman, which actually says that this is the best possible. So it says that whatever 2H coloring I of a complete graph on capital N vertices I will consider, when the number of monochromatic triangles will be at least 1/4 plus some little other times. And I actually prepared a short proof of this theorem, which is not a difficult theorem. So let me try to do my best to present it. And this is the whole proof. So let's say I'm coloring with red and blue, and I want to start with counting the number of pairs, or sorry, for a fixed vertex V, I want to count in how many triples it is contained. That I want to have a neighbor of V and another neighbor, such that these edges are blue or or red. So in other words, so let's say I fix a vertex V, and I want to count the number of pairs A and B, such that both A and B are joined by a blue edge or they joined by a red edge. So what is this? This is at least, well actually there should be an equality here, but it's the blue degree of that vertex, choose 2, plus the red degree of that vertex, choose 2. So I'm counting just, I fix a vertex V, I'm looking how many pairs of vertices are both its blue neighbors or red neighbors, and by convexity, the minimum is attained if the blue degree and the red degree is the same, which would mean it's n/2, and this would be a lower bound. Maybe I'm slightly hiding like the linear terms, but essentially this is the lower bound. And now I need to count the monochromatic K3s. So this will be a little bit harder counting. So I have I have this bound on the number of these triples. So these are triples VAB, but AVB or is a monochromatic path. So I put it here, and for a reason that I explain in a second. And now let us look what can happen. So if I am looking at a triple of vertices, I either see a monochromatic triangle or I will see a triangle that looks like this. In this triangle, I have one such path, namely this one. And similarly here I have this one. In these triangles I have 3 such paths. So every triangle in my graph contains at least one such path. So if I take the lower bound on the number of paths, subtract the number of triangles, I counted each of these triangles once and each of these triangles as well once, but I should have counted it 3 times. So now I'm at 2. So if I divide by half, I have a lower bound, and that's good. So I just included the proof because it's not difficult, and I wanted to. And actually, I should say this is the only proof during the whole talk. So I just wanted to present it. So what I want to be looking at the remaining 40 minutes, at least I believe I was told the talk should be 50 minutes plus some discussion. I want to be looking at the answer to this question in more general settings. In particular, if instead of triangles, I take K4, K5, or more generally, if I take an arbitrary graph which doesn't need to be a complete graph. And because I am a graph limit person or a combinatorial limit person, I want to be looking at this problem using the tools provided by theory of combinatorial limits. So let me briefly say what I will need from that. This is the introductory slide. I try to be gentle. I didn't prepare like 2 or 3 slides, but hopefully there will be enough intuition of what's going on. So the theory of combinatorial limits that started maybe around 15 years ago was developed by Borg-Chayes, Lovász, and their collaborators, and it aims to provide analytic tools to represent large discrete objects. So in this talk I will be looking at graphs, and at kind of a, I would say, a somewhat like a very naive way, what I will be doing, I will be replacing the adjacency matrix of a graph with a function, kind of, with a, I wouldn't say smooth function, but with kind of a function representing the adjacencies. So I kind of prepare here some pictures, so let me try to explain it. So suppose I'm looking at large complete bipartite graphs where 1/3 of the vertices are on one side, 2/3 of the vertices is on the other side, and the edges are between. So this is a large complete bipartite graph. If I look at the adjacency matrix, the matrix will have 2 blocks of zeros and ones between the 1/3 and 2/3 kind of corresponding to the edges between the 2 parts. And now if I look at it, if I say, okay, now I'm looking at it from a very large distance, what I'm going to see something that has 2 areas which are 0 corresponding to the independent set, and 2 areas which I drew with black corresponding to the ones. So I'm looking at the function from 0, 1 squared to 0, 1, such that 0 corresponds to non-edges, 1s correspond to edges, and that function doesn't need to be necessarily 0, 1, as I drew here something with gray. It can have some values between 0 and 1, representing that the edges between those parts are distributed randomly. There's a lot of going on behind, so in order for this to make sense, one needs to kind of think about graph regularity and somehow glue it together with the graphs, but let's just think that this makes some sense, somebody prove it, and I will be, instead of working with finite objects, I will be only working with these objects which in a certain sense are continuous. Maybe better word would be analytic, and I will be thinking that the graphs that I'm getting, the 2H colorings, will be represented by these objects, which will be functions from 0, 1 squared to 0, 1, because I want to think of them as kind of adjacency matrices. I want them to be symmetric. So for me, the origin of the coordinate system will be in this corner, because I want to have the analogy with the adjacency matrix, and the symmetry means that it's symmetric according to this diagram. So this one is the graphon. That's how this limit object is called, corresponding to the complete bipartite graph with parts in the ratio 1 to 2. This one is the complete bipartite graph with parts in the ratio 1, 1, K and N, if one wish. This one has no structure. I have edges somehow distributed, so I put it here mostly to remind myself that the graphon doesn't need to be 0, 1. It can have any values between. So this one would actually, if I take a sequence of Erdős range random graphs, this would correspond to the limit of that sequence. So one can think of it as a graph which has a certain edge density but completely lacks any structure. And this one is a union of cliques, or complete graphs if one wishes to say it that way, one on half vertices, one on quarter, one on 1/8, and so on. And because I want to be talking about some subgraph counts, so if you ask me to count the number of triangles based on the adjacency matrix, what would you do? You would do a triple sum of the product of the entries. You sum over all choices of vertices, and if you have a hit, you check it's a triangle by taking the product of the 3 entries determined by the 3 vertices. And the same goes here. So if you want me to tell you what is the number of triangles, I think of x, y, and z, which like the vertices. So the points of this interval are vertices for me, and I just do the integral. So this means that in the graphon, if I choose x, y, and z in the interval 0, 1, I will kind of get, so I will get 0 here. Here I will get some value which I don't want to shame myself. It will be 1/3 maybe. I believe it can be 1/3, but I'm not sure. Okay, some value which one can compute as a geometric series. And in this one, it will be just the density cubed. So this is all what I want to say about combinatorial limits. I want to have an analytic object which one can think of some kind of like a limit analogy of the adjacency matrix. If I want to count subgraphs, what I may do is that in the matrix I would have some complex triple sum, or more generally if the graph has n vertex, then like n sum, and I will just replace it with an integral. And there's some theory which says this makes perfect sense. Okay, any questions? I know that maybe I should have prepared more slides, but I just didn't want to talk too much about graph limits, and I kind of pushed them on one slide. Okay. So, I want to say a few words about Sidorenko's conjecture, which in particular I want to show that this language of graphons that I just introduced is very convenient to formulate it, and I think it's one of the most major open problems in extremal combinatorics. I don't want to be comparing it, like, let's say, to tetrahedron conjecture or some other big problems, but it's definitely one of the most major problems. And it says that if I have a bipartite graph, when if I look at any large graph, or if I wish to say in the analytic way in a graphon, when the density of this graph will be at least the density of that graph. So I'm looking how many edges I have. So this P I can think as the fraction of pairs that actually do span edges, and it will be at least what I would expect in the random graph. So in the random graph, if I take the Erdős range random graph with density P, if I am counting now, there might be labeled, unlabeled, but let me swipe this normalization under the carpet. Then the Sidorenko's conjecture says that this inequality holds for every graph on W and every bipartite graph H. And there's a more general conjecture due to Skokan and Thomas, which says that if H is a bipartite and contains at least one cycle, then the equality actually holds if and only if the graphon is P. So it's called forcing conjecture because it kind of forces the graph to be, or if one wishes to think about a sequence of graph to be quasi-random. And there's many partial results. I particularly wanted, even if I don't want to state any of them, I wanted to particularly point out the work of Junkun Lee, because he's involved in many results on the recent progress. But in general, the Sidorenko's conjecture is quite open. The smallest open case is the so-called Möbius ladder, which has 10 vertices. On the other hand, it's proven for some graphs that do enjoy certain symmetry properties, and for some additional graph it might have, like, let's say, universal vortex or some other constraints. So I don't want to talk too much about Sidorenko's conjecture, but I would like us to remember that Sidorenko's conjecture says that this holds for any graphon and any bipartite. And I almost forgot to mention that there is also something which is called a local version. So there has been a weaker version proven by Lovaas, and a stronger local version proven by Jacob, Fox, and Van Wey. So when I have a graphon, it makes also sense not only to speak about graphons with a certain density, but I can also add additional constraint that graphon is close to the constant graphon. So let's say I can measure the distance of the graphon from, let's say, the P constant function, let's say in L1 norm or L1 metric. And Fox and Wey actually characterize which graphs satisfy this local version. So there are two possibilities how to say what local means, and I will, at the end of the talk, I hope to talk about the common graphs in the local setting. And one way is that if I choose the perturbation, when I want to be guaranteed that for that perturbation, if I don't perturb too much, then when I will not decrease the density. The other one is when I'm looking at the ball around the P constant graphon. So we proved a stronger version for the ball, which actually matches the characterization for the directions, and all that matters is the parity of the length of the shortest cycle. So if I am looking at my graph, it satisfies the local version if and only if it has no cycles, or the shortest cycle has even length. And as you see, I prove here 2017 when the result was announced, but we actually using some, I wouldn't say tools, but some similar ideas, and I do understand why it takes 6 years to write up. I have understanding for that. Okay, so back to our problem. So we're looking at Ramsey's theorem, and now I can actually reformulate the question: what is the number of monochromatic copies in terms of the graphon? So what I can do is I am looking at the minimum value of, so I fix graph H, and I wish to be looking at the minimum value minimum value of this sum, where I will think of W, let's say, as so what I'm looking at the 2H coloring of a complete graph. So I will think, let's say, of W as the red color, and when the complement, which is nothing else than 1 minus W, will be the blue color, and I want to know what is the minimum value of this sum. And we have already seen Goodman's bound. So the Goodman tells me that for any graph on W, this inequality holds, and actually if we inspect the proof, we can actually get the graphons for which the equality holds. So let me, I can maybe, like, if I can, I'm happy to discuss afterward. And Erdős in 1962 made a more general conjecture that actually every complete graph has the same property as the triangle. So he conjectured that the number of monochromatic copies, let's say, of K4 is also minimized by the random 2H coloring. And the same holds for the monochromatic copies of K5, K6, and so on. So let me keep this conjecture. So I just wanted to say again that I have here formulated in the graphon language. So this is the conjecture of Erdős. The random 2H coloring is minimizing the number of monochromatic copies of a complete graph, and there was a I didn't say that nicely. So there was a more general conjecture of Bohr and Rosta, but for that let me actually make a definition. So I will be calling a graph common if the random 2H coloring minimizes the number of its monochromatic copies. So a graph is common if this inequality holds for every graph on W. So in particular, the conjecture of Erdős says that the complete graphs are common. In case you're wondering why it's called common, so I actually wondered too, and I was told that because if it's not common, there's a coloring where it actually is below the random threshold. So common means it commonly appears in the coloring, where commonly means at least as many times as in the random one. At least this was the explanation I was given when I asked why it's called common. And Bohr and Rosta conjectured that more generally every graph is common. And based on how I said it, it's you may guess that basically everything is false. So Sidorenko disproved Bohr and Rosta's conjecture by showing that triangle plus an edge is not common. Thomason showed that no complete graph except the triangle is common, and more generally any graph containing K4 as a subgraph is not common. And there's also a result of Jacob Fox, which I believe was one of his very first results. This is one of his very first papers, and the result says that if one has a non-bipartite graph, when by adding a sufficiently long path, that graph becomes not common. So if one has a non-bipartite graph, by actually adding not only a path, but by adding any sufficiently large tree and appending it to a single vertex of it, it may be a star or it may be a path, then graph will stop being common, which is a more general phenomenon than this. We have a triangle which is common, but if I append an edge to one of the vertices, I have one vertex of degree 1 joined to one of the vertices of the triangle, when it's not common. So basically the last thing actually says that common graphs are rather uncommon. Well, it's like, sorry. Like it's like if I take a random graph and it will contain K4, so that's a true statement. So now let's look at which graphs are common. So the Sidorenko's conjecture actually says that in every density, if I have a graph of a certain density, then the number of copies of a bipartite graph will be at least what is given by the density. So if I have, let's say, a red and blue coloring, then the number of copies will be at least the density of red color, power to the number of edges plus the density of the blue color, and by convexity I immediately get that any such graph should be common. However, as far as I know, I don't think there is any bipartite graph which is known to be common and not known that the Sidorenko's conjecture holds. So the Sidorenko's conjecture says that every bipartite graph should be common. If Sidorenko's conjecture is known to hold for a particular bipartite graph, that graph is also known to be common, but I don't know, it might be my lack of knowledge of the literature, any bipartite graph for which it would be known it's common, but it wouldn't be known that the Sidorenko's conjecture holds. Of course, if Sidorenko's conjecture holds, there should be no such graphs, but would actually, for which Sidorenko would fail and the graph would be common, but in principle it might be easier to prove a graph to be common. Yes?
I think maybe I forgot. I thought, what was the same in the Sidorenko's conjecture again?
Sorry?
I thought that Sidorenko's conjecture was that bipartite graphs are common.
No, Sidorenko's conjecture says something stronger. So Sidorenko's conjecture says this. So Sidorenko's conjecture says that I don't need a partition, but I'm just looking at one color class and I find enough copies there. So it says that if I will be looking at the red color class, I will find the number of copies given by the density of red edges.
Yeah.
And if I'm looking at the blue color class, I will find the number of edges given by the. So it's a stronger statement. So in principle, it might be easier. So so if one looks. So basically, if H satisfies Sidorenko, then it would be telling me that this is at least the density of W powered to the number of edges. This is at least the density of 1 minus W powered to the number of edges, and this will be minimized if I have both same density. Okay. So it makes sense in a certain way, unless one wants to prove Sidorenko's conjecture, to look at non-bipartite graphs. And actually Sidorenko proved that every odd cycle is common, which is not a super hard result, but also not easy. When Jagger, and Thomason proved that every even wheel is common. So even wheel is an even cycle with an extra vertex adjacent to all vertices. And as you may see, these graphs are free chromatic. And it has been open for a long time where there was a 4-chromatic common graph, which was resolved, and you may see a certain gap in the years, by Hamed Hatami, Honza Hladký, Sergei Norin, and Sasha Razborov, and myself. And we showed that the 5-wheel is common. So 5-wheel is one takes an odd cycle of length 5 and put an extra vertex. Now we also know that the 7-wheel is common, but I don't believe that there's a proof that all odd wheels are common, even if it's generally believed. It looks now strangely at me, but.
I thought odd wheels is known.
Sorry?
I thought odd wheels is known. Okay.
I'm not sure. No, you're right. No, I don't think so. So what's known is that if you have a Sidorenko's graph with a small number of vertices edges, like a sparse Sidorenko graph, and you had an extra vertex, then you would be common. But not for non-Sidorenko graphs. I don't think that 9-wheel is known to be common. It might be again my lack of knowledge, but I believe that 7-wheel was proven, and I would assume. Okay, I don't want to attribute it to somebody else. I have a suspicion which paper it is, but I don't think that 9-wheel is known. But I might be not updated. So clearly, the question is, one can construct common graphs of arbitrary large chromatic number. Yeah. So in particular, it's not obvious how to get a little bit farther than with 4, because 5 will actually The only proof known is using the flag algebra, so it's a highly non-combinatorial proof, computer assisted. It's a proof, but some people would be dissatisfied when it doesn't bring like insights, because it's just with certain optimization program or certain optimization problem has a solution that can be verified by a computer to give a proof, but we really don't understand what's kind of going on in the sense that perhaps this is not so terrible, but but still on the boundary of human verifiability, but even if we verify, it would be just like some inequalities, we wouldn't understand what actually is going on.
Sorry, you said that was for the 5-wheel?
Yeah, for the 5-wheel and for the 7-wheel, it's also flag algebras. But which makes me suspicious that there's no proof of 9-wheel, because then you perhaps would need to either like apply them somehow in a smart way, or do a human proof of smaller wheels. So there was this question: what about chromatic number at least 5? And that's actually the main result I want to mention in this talk. So with the question has been open for like I believe on 25 years, because it appears in this paper from 96, and with Honza-Volec and Fanway we prove that there exists a connected L-chromatic common graph for every L. So I will not be like presenting the proof, I will just say how the graphs look, and I try to explain what is the kind of the main idea, but I should warn you, it will sound simple, but the paper is like 50 pages. So the idea is simple, but there's lots of technical things that needs to be resolved. So this is the construction. So we actually proved something stronger. So we proved that for every graph that has graph at least 30, if one takes that graph and a sufficiently long path, and when one has a sufficiently large complete bipartite graph, then this graph is common. So the quantification actually is that for every h0 there exists n0, such that for every complete bipartite graph with at least n0 vertices on every side, for some technical reasons it's better to restrict the numbers of vertices to be even, there exists some m such that this graph will be common. So I have a choice of this graph as long as its graph is sufficiently large. Once I have chosen that graph, I need to put here sufficiently large complete bipartite graph, but I still have a choice how large, but from a certain threshold on. And once I have fixed this, then the length of the path needs to lie in a certain interval, because it cannot be too short and cannot be too long for some reasons coming from the proof. And the proof is based on the spectra of a graphon. So basically what we're doing is we look at, let's say, the red color class, we look at that graphon, and we look at its spectrum as an L2 operator. So that I think of it as an operator acting on L201, and I look at its spectrum. And why this is useful? So first of all, the spectrum describes me the number of cycles of like 4. So because like if I have an adjacency matrix, then the number of cycles of length 4 is just the sum of the 4th powers of eigenvalues, and the same actually holds in the limit. So it's a nice operator, so-called Hilbert-Schmidt operator. It has a countable spectrum, so it makes sense to actually talk about the sums of the powers, and then it can be actually shown that the number of these copies, the number of these k2n, is at least the nth power of the sum of the 4th powers of the eigenvalues. So that already brings me some link. So somehow, if I am close to the random, I will just have the lambda 1 to be the density, and the remaining eigenvalues will not be present. But if I have some structure, when lambda 1 still be at least the density, but I have the remaining eigenvalues that will actually push me the lower bound on the number of these copies up. So what we did is we defined two functions, f and w, which kind of corresponds how many rooted copies of A0 I can find at a particular vertex, and how many rooted copies of this complete bipartite graph I can find at a particular vertex. So if I fix a vertex of my graphon, when fx tells me how many ways I can extend it to a copy of A0, and gx tells me how many ways I can extend it to a copy of this complete bipartite graph. So in particular, if I would just take this scalar product of j and g, where j is the function which is all 1, I would just get the number of copies because I'm integrating over all the choices of the root. And now, what is the number of copies of this graph? Well, I have this path here, but there's nothing else than applying this operator w. So if I think of it as a linear operator and I basically walk along the path, it's just the same thing as applying it as a linear operator to g. And once I finish walking along this path of length m, so I applied m times, I just like need to do the dot product with the rooted copies of the other graph. And again, like the spectral decomposition is very nice because this is nothing else when I need to decompose g into eigenfunctions. I have the eigenvalues, I need to do something, and that something means that I need to look like at different possibilities, what might be the eigenfunctions, how they would relate to g, what might be the eigenvalues, and analyze in each of the cases that I either get enough or I can do something else, because occasionally I need to recurse and go to a smaller graph form. So I don't want to talk more about the proof. I just wanted to give a hint that there's some spectral arguments in it. I wanted to hint why these spectral arguments are particularly useful in this setting. If W is far from being so let me maybe say one more word. If W is close to being random, then basically everything what I see here would somehow be close to what I would expect in the random setting. If W is far from being random, then f actually can be quite small, but I will gain a lot from this expression. So that's kind of the paradigm we're playing. So if we're close to the random setting, we basically apply like lower bounds just coming from the random setting. If we're too far, then I'm gaining a lot here, while I can lose a lot on this side, and I have this path just to kind of make these two copies independent in a certain sense, because like the longer path, more independence. However, if I'm too sparse in the color, it can also happen that I will not manage to connect well. If you're wondering about this 30, I would believe that we can decrease it maybe at least all the way to 6 at the expense of adding more technical details, but we didn't have any motivation to decrease it because we didn't have any application. And I also didn't say how it implies the original theorem, but there's a classical result of Erdős which says that when there's high chromatic graphs, so basically we just choose this H0 to be any graph with chromatic number L of graph at least 30, and such graphs are known to exist. So that's all what I wanted to say about the main result. If I lost you, and we may reconnect. If it was too much blah blah, then I do apologize, but I really didn't want to go into more technical details. I just wanted to hint why these spectral methods might be useful.
Can I ask something? So
Yes.
when you choose n, do you choose n based on m, or is it?
No, the other way around. So first, n is chosen based of H0 because like I want this graph to kind of balance possibly small number of copies of H0. So larger H0, I will need this graph to be larger. And when the path is here to make these two copies kind of independent, and we actually, this m actually cannot be like chosen also too large once we fix n. So there's kind of like a gap, but if we choose it if m is too small in terms of A0 and once n is fixed, then we don't have enough independence, because it may happen that we have some bipartite bit, but that bit will not contain a copy of H0 because H0 is non-bipartite. So we need somehow to walk somewhere else to find our copies. But if m is super large, then it also may happen that by this walking, because like this W may be somewhat little bit sparser than we needed, we lose too many copies. So somehow like there's some delicacy, but what happens first is that n is chosen large based on H0, that somehow this complete bipartite graph its number of copies will outweigh the possible loss of the copies of H0, because A0 is definitely not common, so I may have fewer copies. On the other hand, it's well known that for complete bipartite graphs, the number of copies is growing heavily once one gets from the random setting. And when this path is then made to correct.
Was there, you mentioned a result that said that you can add a long path to a graph and make it not common?
Correct, not common, yes.
Okay.
But that path needs to be a path which ends at a vertex of degree 1, which
Right.
fortunately we don't have here.
Right.
Yeah. Which also implies that there's no chance to have a characterization of common graphs in terms of forbidden induced subgraphs. Yeah, because like basically any graph of graph at least 30 is an induced subgraph of a common graph, but at the same time by adding a sufficiently long path to it, one can make it uncommon. So there's no chance, like either by saying like doing a characterization by induced subgraphs either way, like even being on the common or the uncommon side. Good. So I have a slide on the generalization to more colors, so which is what you would expect. So H is K common if the random KH coloring is the minimizer of the number of monochromatic copies. Sidorenko's conjecture implies that every bipartite graph has a Sidorenko property, and therefore it would be K common for all K. And what is actually interesting is that it actually holds the other way around. So if I have a graph which is K common for all K, it actually has a Sidorenko property. And that's actually what I discussed with some people in the last 2 hours. That basically we reproved the other information. And of course, one may ask about the K common graphs which are non-bipartite. So it has been actually an open problem even to find a free chromatic one, because for example, triangle is not free common. And with John Noel, Sergei Norin, Honza Volec, and Fan Wei, we constructed non-bipartite K common graphs. And they actually are quite simple. So one takes a complete bipartite graph, and in one of the paths, on every second vertex, one puts a copy of C5. So we actually do believe that it would be enough to put a copy on C5 on one vertex, but we didn't manage to prove it, and this also serves the purpose. And our result with Honza, Volec, and Fan Wei also generalizes to the setting of K common graphs. So basically the same construction with just a little bit of extra work, but maybe that adds 1 page to this 50-page paper. So it's not like terrible. Says that if one takes any high curve graph and does the same construction, but it will be K common. So I want to say a little bit about the local setting. So I already mentioned Sidorenko's conjecture, and the local setting essentially asks what happens if the graphon or the coloring is close to the random. So in the maybe like in the non-analytic way, it might be a little bit hard to talk what it means. But when I'm looking at the graphons, then what I can think of I can think of a graphon as the constant graphon plus some perturbation. This perturbation doesn't need to be non-negative, it can be also negative as long as it's symmetric. So I kind of perturb it, and I may be asking what happens if this U is small. And one can think small, like the cut norm is the standard norm in the area of combinatorial limits, but one can think of it small, let's say in L1 norm or an L2 norm as well. And as I mentioned, Lovász and Fox and Wei, they consider Sidorenko's conjecture in the local setting, which is not what I prepared the slides here. So let me mention the results. So I already was indicating that Lovász kind of was looking at the direction. So basically, for every perturbation where exists epsilon 0, such that if I don't go too far with that perturbation, I will never decrease the number of copies. And what Jacob and Fan did was that they actually showed that this epsilon 0 can be chosen independently of the kernel. So there exists epsilon 0 such that for every kernel whose norm is not too big. I put here the cut norm, but it's quite safe to think of L1 norm when that perturbation will not decrease the number of copies. And in both cases, the characterization is if and only if there's either no cycle or the graph is zero. And it similarly makes sense to look at the common graphs in the local setting. So I will be looking at the coloring, and I will put bound on a perturbation. So I will be saying that H is locally common if and only if I'm looking at the number of copies, that let's say I increase in one color by U and I decrease in the other color by U, then it will not decrease below the bound given by the random color. And Choka, Hubai, and Lovas, they actually look at both settings, and they show that unlike in the Sidorenko's conjecture, there are some graphs which are locally common in one, but not locally common in the other. So, and the example is if a graph contains K4. So if a graph contains K4, it is not locally common in the stronger sense, but is locally common in the weaker sense. Yeah, so the stronger sense is that there's a universal epsilon 0. The weaker sense means that epsilon 0 can depend on the perturbation. And what we did with Robert Hancock, Matthias Kearns, and Honza Volec, we actually look at this weaker setting, and we think of this as that this expression is actually some polynomial in epsilon. And when we can analyze the first 12 expression in the Taylor series, we did a full characterization. So I put here some results, and I will show the theorem or the statement of the theorem on the next slide. So for example, if H contains C4 or C6, when it's common, so in particular, if it contains C4 and we don't need it to be an induced copy, when it also, if it contains K4, it contains C4, so in particular, it implies this result. But we also showed that, for example, if there is no C4, C6, or two triangles sharing a vertex, but there's a triangle and a 5 cycle sharing a vertex, then it's not locally common. And let me show. So basically, what we did is we look at the terms which correspond to the powers of epsilon up to 12, and based on these terms, what we may do is we say it's locally common, it's not locally common, or one needs to look at additional terms at this Taylor expansion. So it may be either way, but we cannot decide based on what we see. And this corresponds to looking to a certain subgraphs, and these are the statements of our theorems. So class 1 and class 2 means locally and non-locally. Class 3 means you need to go to the next level. So this is corresponding to 10, and this is the statement of the final theorem. So one kind of comment here, and there's like you look at whether there's like two triangles sharing a vertex. If yes, then look at whether there's a 10 cycle. If not, then so basically it's kind of like a program. And as you may see here, so it's not only that one just do some inequalities like or looking like is there this or this. Here there's also like some kind of polynomial expression, and there's another polynomial expression which is like a matrix, which one multiplies from left side and right side by the same vector, which is also given by densities. So what was actually interesting is that this looks like, this looks like quite monumental to prove, I would say, but it wasn't as bad as it looks. Actually, the statements I wouldn't say are longer than theorems, but what was interesting is that both the non-common and both the common arguments are based on spectra. So basically there's not a single combinatorial argument, everything is just based on the spectra. So if we can prove that something is locally common, we get it from the spectrum. If we can prove that something is not locally common, we realize what the spectrum should fail to satisfy, and we have a general method for constructing graphon with a spectrum that actually has the property to show it's not locally common. So I don't want to, I just wanted to indicate that classification of locally common graphs, whereas unlike the locally Sidorenko graphs, which actually had a very simple classification through the GIRF, but this looks like a more like challenging problem. However, it may be but there might be some general theorem saying just like look at the spectrum, and if the spectrum satisfies some condition, then that's it. So open problems. So we constructed L chromatic common graphs for every L. I would like to point out that our construction is connected. If we drop this connectivity, then things will become slightly easier. It's still non-trivial, but we thought it's cheating, and we could do connected, so we did connected. When Sidorenko, I hope I'm pronouncing his name correct, this audience I should be careful, and Junkyun Lee, they actually managed to boost the connectivity. So what they did is they took our construction and applied some recursive way of boosting the connectivity. So they showed that there exist L chromatic graphs which are arbitrarily connected, which like if it's not possible just to do like, I mean, if we take our proof, it wouldn't give it because we need this path because we kind of really walk along it, but it's possible to do some kind of product construction or product operations, taking our example and then boosting the connectivity, which was actually we posted this as an open problem in our paper, and we have been very happy to see it was quickly resolved. However, let's make things a little bit more challenging. So what about if we also require high girth? So for us it was very essential to have this complete bipartite graph, and it would be possible to get some other graphs with high girth, but they wouldn't have like quadratically many edges, and it's somehow we need also some kind of at least like superlinear number of edges. We need some kind of density in this part which is boosting so if you remember, the construction was the arbitrary graph, long path, and this complete bipartite graph, and for us it was important that this complete bipartite graph has superlinearly many edges in the number of vertices. So we would need something with high girth where we have a control how it relates to the spectra, and at the same time is not sparse. And we don't know how to do it. So the obvious candidate, of course, is to take, let's say, one subdivision of the complete bipartite graph, but when the number of edges is linear in the number of vertices, because we have a lot of vertices of degree 2. And of course, classification of locally common graphs. I might have scared you by the previous slide. On the other hand, as I said, like all the proofs are fully based on the spectra, so it may happen that there would be maybe not a nice structural characterization, but there would be something nice that one can say about the spectrum of H, or maybe somehow related to the graphons, and basically get a somewhat indirect characterization, which indirect classification in these terms. I think I was a little bit longer. I also started a little bit late, so I think it's time to.
Thank you. Any questions?
So you mentioned, so every graph that contains K4 as a subgraph is not common.
That's correct.
You show that every graph of girth at least 30 is a subgraph of a common graph.
Uh-huh.
So I wonder, is there any way to characterize graphs which are subgraphs of common graphs?
Graphs which are subgraphs of common graphs.
Is it possible that this is just K4 of free graphs?
I would not be thinking so, but I don't have a quick example. Like I would assume that something more complex with like gluing somehow triangles together might be another obstacle. But a quick answer is I don't know. But it's a good question. So basically somehow I would be thinking that if something contains a lot of triangles somehow glued strangely to each other, but strangely perhaps shouldn't mean like real, but I don't know. Yeah, because 5 is common, but maybe like, yeah, I don't know. Okay. The simple answer is I don't know, but I think triangles in general would be a problem.
Okay.
But, so I would be very much surprised if K4 is the only graph with this property. But
Yeah.
But
But you think that maybe Girth 6 is enough, like you said, maybe this.
yes. So I do believe that we can actually push this, like, I would even say Girth 5. So with Girth 4, I would start being careful, but I would even think that, okay, with Girth 5, you know, if you highly motivate me, and I don't think it will be $5 that Hong promised earlier today for proving something, then, you know, I will prove Girth 5 for you here.
Is there like a specific obstacle with Girth 4?
With Girth 4, what I'm worried is how it will start interacting with this.
Okay.
Yeah, but I think it will still be okay, but
Yeah.
yeah. So basically, like somehow, well, that's my worry.
Okay.
But I think it will still go through. But
Other question? So you use the spectral decompositions and maybe, I'm trying to guess the method of the proof. So this is
you mean for this or the?
yeah, for this, but you like how much of the proof is like a technical computation of integral and inequalities?
Not so many integrals, lots of inequalities. I think most of it. So there's some idea somehow, like if so basically, like there are three cases depending on like the spectrum, like how far is the spectrum from the random, and also how far is is particular this eigenfunction from the random. Yeah, and somehow like the spectrum may not differ so much from the random, but if the eigenfunction does differ, then it actually indicates something about the structure of the graphon, and maybe what we may want to do is actually to kind of apply some kind of recursive argument. So there's it's an interplay between the spectrum and the structure, but there are lots of estimates because somehow we need to lower bound various quantities. So there are ideas, but the ideas, in order to make them to a proof, it requires some non-trivial technical skills, or maybe skills like technical manipulations.
Does it also, do you plan to work for K common thing or?
Well, we already did.
Yeah, oh I see, sorry. Yes,
Yeah,
that's right.
this K common like edit maybe a page,
So
so it wasn't like so terrible. Yeah, so basically like, I mean I cheated a little bit because like what we try to do, we try to find in every color the number of copies that the density of that color would give us, and but sometimes we may fail, and if we fail, then essentially the reason is that we have a large complete graph in the other color. But if we have a large complete graph in the other color, and then because we have superlinear number of edges, then in that color we find enough copies. So basically that's the reason why we need here to be superlinear, because we don't have a control. We can control how large this part somewhat will be, but I need to have a boost in something. And that boost is that I have so many edges here that if I find something which is almost a clique, I will just win, because I maybe lose something on the number of vertices, maybe it's 1/100, but if basically I can forget the edges. So that's the reason I need like superlinearity. And basically if I have more colors, then instead of finding a clique in one color, I will say there's a part where I don't see one of the colors, so actually I go to k-1, and this adds like just like little bit of induction, but it's just a page in the wallpaper. So it didn't really make it more complex.
Do you know if, can you find graphs that are K common but not K plus 1 common for other Ks besides 2?
Good question. I would say that for every K there would be one, and the answer is yes. Yes, this graph is definitely 3 common. I'm not sure whether it's 4 common, but it's not K common for every K.
Right.
So the answer is yes, I can
Yes.
find it for some K,
So
but don't
for
ask
some
me
K.
which one.
Yeah.
Yes. But if you ask specifically, then I don't think so. I mean, I wouldn't be surprised if this graph is actually not 4 common. No, I actually. Actually, not for every k, but for infinitely many k's, I can find it, because what we did is, yeah, sorry, I should have remembered the results better. What we showed is that for every k, if I take this graph sufficiently large, it will be k common. So I can, for infinitely many k's, we can find graph which is k common, but not k plus 1 common, but we just don't know which case.
Any other questions?
Is the k common result also can be generalized to high connectivity, or in this paper just for 2 common?
I think it could go through, but I don't want to guarantee it. I believe it would go through, because it's just based on convexity, but the result claims common. So their paper, I believe, claims common. I do apologize if I don't remember it well. But the simple answer is I don't know. But I would believe there's a good chance. But I don't know. It's a simple answer. But no, I don't want to say something that's not true on this spot. Because on one hand, I kind of wonder why they didn't claim it for k common, but maybe because we only asked for common. But like now, when I'm thinking about the steps, I don't see an obvious problem, but there might be something I'm really overlooking. And, it's sometimes hard here to be thinking of on the spot. So.
Right. Maybe we should stop. Okay. So let's thank the speaker again.